Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be continuing our talk about the system of linear inequalities, this time by talking about the feasible region. In particular, we're going to talk about what the feasible region is and some applications that we can use for this type of problem. Now first, we should go and define what the feasible region is, and remember, we're talking in terms of a system of inequalities. So remember that a system of inequalities, let me write that a little neater, that a system is when we have multiple inequalities that all constrain the variables. Okay, we have multiple inequalities that all affect what the variables can be. Okay, the variables have to satisfy these different inequalities in a specific way. The feasible region is the overlap of all the inequalities. So we have multiple inequalities. The area where they overlap is the feasible region. This is the intersection, okay? So the feasible region we're going to define as the intersection of the solution sets of all the inequalities in the system. So what we're saying here is that when you graph a linear inequality, you shade one side of the boundary line and you shade all of the solutions. When you have a system of inequalities, when you have multiple ones, you're shading a bunch of different areas. We want where all of the areas overlap. We want the intersection for all of the solution sets, okay? That's what the feasible region is. It's just a more specific term for intersection. Now let's take this idea of feasible region and let's actually go through an application problem to see if we can identify what this area is. So in this problem, we're talking about a store selling two types of toys. There's type X and there's type Y. So imagine you're running a toy store and they only sell two different products, okay? Now the owner pays $8 and $14 for each 1 unit of toy X and 1 unit of toy Y. So if we're the owners, it costs us $8 to get toy X in and $14 to get toy Y in. Like we have to buy it from a wholesaler to sell it, and this is how much it costs us. Now, the owners estimate that no more than 2,000 toys will be sold every month. And this is usually found based on historical data. You know, as you run a business, you tend to realize, okay, we don't have infinitely many sales each month, right? We tend to stay in a certain boundary area. So we can estimate we're not going to sell probably more than 2,000 toys in a specific month. And we decide, you know what? We don't want to invest more than $20,000 in inventory, meaning I don't want to buy more than $20,000 worth of these toys. Because otherwise, I'm spending way too much money and I might not be able to sell all of these. So here are some constraints we have. I don't expect to sell more than 2,000 toys, and I don't want to spend more than $20,000 on buying these toys. I have to spend $8 and $14 on just getting these toys into the store. Like this is how much it costs me just to get them so I can sell them. What we need to do with this information is graph all possible quantities for each toy type that the owner could purchase. So if we're saying that we don't want to spend more than $20,000 and we don't expect to sell more than 2,000 toys, we need to figure out what are the possible number of what are the possible combinations we could have of each toy. We could have maybe just one toy of type X and one toy of type Y. And in the whole store, we only have two toys. That's a possibility. That keeps us under 2,000 and under 20,000. But we can have other combinations. Maybe we have 10 of type X and 20 of type Y. That keeps us under 2,000 total toys, and it would keep us under spending $20,000. The point is there's a lot of possible combinations. We need to graph all the possible combinations of how many of type X and how many of type Y toys we could have. So to do this, we first need to write an inequality that expresses how the total amount of toys sold in a month is no more than 2,000. Okay? Of all the X and Y toys that we sell, we don't expect there to be more than 2,000. Okay? How can we write that as an inequality? Well, we can start by saying, let X be the total number of type X toys. So X represents how many of these first type of toys that we have in the store. And let Y represent the total number of type Y toys that we're going to have in the store. Okay? So X represents how many of these first type of toys we have. Y represents how many of the other type of toys we have. We want to say that the amount of toys we have in store should not go above 2,000. So X plus Y, this is the total number of toys we have in the store. All of type X and all of type Y, that needs to be less than or equal to 2,000. Okay, I could have 1,000 of each. I could have 100 of each. I could have 10 of each, right? I could have 1,500 of one and 500 of the other. All that we're saying here is between both of these types combined, don't have more than 2,000 items in inventory, okay? Don't have more than 2,000 toys at once. So here's our inequality for that. Let's take a look at the next situation where we now want to write the inequality that discusses the cost or the investment. Write an inequality that expresses how the owner will not spend more than $20,000 on all of the toys. So we don't want to spend that much money. Again, we can say X is the total number of type X toys sold. Y is the total number of the other type of toys sold. So how can we say that for X and Y, how can we say that we don't want to spend more than $20,000? Well, part of that comes into remembering how much it costs for each type. So for all of the X toys that we had to spend $8 for each. And for all the type Y toys, we had to spend $14 for each. So this right here would give us the total amount of money spent. This needs to be less than or equal to $20,000. We don't want to spend any more than $20,000. So here are our inequalities. We have them set up to represent the constraints, the things that are affecting how many toys we purchase for each style. So we have our two inequalities, one for the total inventory, and then now one for the cost. Let's go ahead and see if we can plot these graphs. I'm going to go ahead and use Desmos. So here in Desmos, you can see the two inequalities. The first one in red dealing with us not spending or not purchasing more than more than $2,000 in inventory. So we're not holding more than 2,000 toys at one time. And the blue inequality represents that we're not spending more than $20,000. Okay, so where is the feasible region? Where is the area that satisfies this problem? And you should see it's going to be right here in this overlap region, this almost purple-like area. This overlapped region here really demonstrates all the possible combinations that you could have for x and y. Any coordinate point in here, you can go ahead and pick any one of these coordinate points. You can plug it into both inequalities and it will work, okay? So that's the idea of the feasible region and what's going on here. It's really just the intersection of multiple inequalities. With that said, that's the majority of what I wanted to go over today. If you have any questions or comments, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video or if you have any questions or comments. And until next time, take care.